Hello again and welcome to Cyphera's Cryptography Under the Hood webinar. Today we are going to go through how to secure the startup of a digital system and how to build trust from the ground up. I'm Valtteri and I will be your host, and this time I will actually also join the webinar and talk a little bit. But first, let me introduce Cyphera real quick for those who haven't heard about us yet. So Cyphera is a Finnish company founded in 2017. We design hardware-based security solutions using standardized cryptographic algorithms, and we offer those implementations and as intellectual property cores, or as we say, IP cores. Our IP cores include cryptographic algorithms and protocols, and they can be easily integrated into ASIC, FPGA, or SoC platforms. For more information, please visit our websites at cyphera.com. And just a couple of practicalities about this webinar. So please send any questions at any time using the Q&A inbox found in the Zoom. And for your information, this webinar is being recorded and it will be accessible later along with the material with the previous webinars in our website. And now we can move to the actual agenda. So let me introduce today's other speaker, Petri Ehkonen. Petri has over 30 years of experience in various technology industries. His expertise covers engineering, project management, and marketing and sales positions. Petri holds master's degree in electrical engineering at Aalto University and bachelor's degree in social services and healthcare. The stage is yours, Petri. Please go ahead.
Thank you, Valtteri. So it's my pleasure to today discuss about quantum resilient secure boot, and I will be creating actually basis going through a very simple, not simple, but very clearly building our agenda and the trust. So the agenda roughly is that I will go through how this trust is created on the computing platform. Then a little bit about the secure boot and the building blocks that are needed there. And then Valtteri will go through in real life example encrypted secure boot. At the end, we will have some discussion with Valtteri, and naturally, I hope that you have been sending some interesting questions for us. So starting from the really principles, so computing platform typically consists of some sort of non-volatile memory. It means that it possesses the data that is needed by the system, and it stores the memory, the content, even when the power is down. So it has a non-volatile memory. It's connected to the IC, so integrated circuit IC could be CPU or FPGA, which is performing the power-up sequence. So it's loading information or binary from the non-volatile memory. And there are other components on the computing platform, like external CPUs, DRAMs, power supply components, clock components, radio frequency components, networking components, and sensors and others. So this is what we talk about computing platform. It could be embedded, or it could be actually it's kind of large, even larger scale block computing platform. And now, the first step when we start looking for what is actually are the essential elements is that if you have this non-volatile memory that has boot image of the system inside of it, you can see from even from the simple schematics of the layout that it could be programmed through the IC or maybe some other component through electrical interface there. or even if it's not powered up, it could be programmed through this external programming interface, like physical connector. And so it means that this non-volatile memory could be changed by multiple parties. Even when the system thinks it's on the power down, it might be that somebody is actually programming it through this programming interface. And this power up sequence, when this system is powering up, it could include several bootloading stages. So it could be powering up multiple devices, maybe through this one IC that is on the schematics and there's a black. So that's actually the reason that because we would like to be sure that this binary inside of the non-volatile memory or on the memory where this system is powering up is something that we can trust. So that actually then requires that we will use cryptographic algorithms as a foundation to build this information security. And the information security is the binary security. So in that sense, we have to take this binary and we have to put it through some cryptographic algorithms to have additional information or modify it if needed, so that we change the binary itself to be so that we can protect the content, the information inside of the binary. And of course, so at minimum, that information has to be what algorithms has been used to protect it. And then on this IC, this could be CPU or FPGA, we need some kind of trust validation method. So it should be something that checks the binary that is matching the security schemes that have been created are met. So for example, so it can be actually checking only the IC CPU itself if it's a hardened block on the IC, or FPGA bootloader system that could be loading other components. So our key goal here is that to make sure that this binary is not tampered with, and every component on this system is powering up on the trusted mode. So that means that now we have a kind of the foundation for the trust on the system. Pretty soon, actually, Valtteri will jump in and go under the hood, how this is done in practice. But I need to, before we go there, because we are using cryptography for these protections, I need to remind one of the very fundamental and contemporary issues, that is the imminent quantum threat. So the algorithms that we are talking here, they operate on bits. They are computing numbers on the finite fields, and that's the cryptography that we use. And some of these algorithms, namely asymmetric algorithms, could be in danger when quantum computers are powerful enough. But that's not only that when they are powerful someday later, but somebody could harvest, so collect the information today and decrypt it later. That might not be actually so harmful maybe for binary images, but the similar approaches and algorithms are to be applied in the future. So now it's quite typical that when we are using these algorithms for protecting the binary, we actually use the digital signatures. So it means that the elliptic curves and RSA, which are said to be in danger with the quantum computers, has to be something that we can help with. And so this is what we are calling post-quantum cryptography. So it means traditional computers protecting the information with new algorithms or new scheme of algorithms. And so now this transient to this quantum resilient cryptography is happening, and one way to go for that is to use hybrid models where we take the benefit of the previous algorithms or the existing established algorithms with the new PQC algorithms. So the secure boot could be a combination of protecting confidentiality, integrity, and authenticity. And some of the CPU and FPGA vendors, they actually provide relatively good power-up protection schemes. They are efficient and they are secure, even though there are shown weaknesses with some of these power-up protection schemes. Also, these algorithms that are implemented, they are predefined, so you can change them afterwards. So they are not versatile and they are not agile, so you could not change the algorithm that easily. And now, if you're looking current offering on the CPU and FPGA markets, they typically are not PQC, so post-quantum cryptography compatible. There are some nice attempts to do that, but they are not yet there. And when these actually are operating these power-up sequences, it might be that they have been using very, very deep third-party software stack when they are doing the validation or even the creation of the security. So in that sense, I think what is now happening is that more and more we need agility on the systems, and also we need to have the PQC implemented on this for this platform protection. So now, if I'm looking for, this is like a high-level view. So to enable the secure boot, how we are looking today, is to use the established cryptographic algorithms. That means elliptic curves, RSAs, and so on. And also adopt the new quantum threat mitigation schemes, new algorithms that are standardized or to be standardized. And take best of both. So deploy the hybrid cryptographic protection. So relying only one, the new or the old, might not be good. So combining two strengths doesn't make either one of them weak if other one is weak. And also, when you are securing this power-up sequence, it's always a good idea to use verified, validated implementation of IP cores. And if possible, to go for hardware-based solution when securing the boot, so that it's very hard to tamper with later on. But now it's time to go under the hood. Please let me bring back our host, Valtteri, who just happens to be also outstanding developer in our company, and my colleague as Master of Science. So please, Valtteri.
Yes, thank you, Petri. This is actually very exciting already because we have a real-life working product already. So let's go through it piece by piece. And first, let me go over a little bit of the basics. So we need to understand what is asymmetric cryptography that Petri has already mentioned. So asymmetric cryptography is basically the cryptography where you have two keys. You have a private key and a public key. And from the traditional cryptographic algorithms, these asymmetrical algorithms include, for example, elliptic curves and RSA, for example. And from the PQC side, so the post-quantum cryptography, we have MLDSA and SLH DSA. And MLDSA stands for module lattice-based digital signatures and algorithms, and SLH is stateless hash-based digital signatures and algorithms. So both of or all of these asymmetrical cryptographic algorithms, they generate a key pair from a random seed that typically comes from a TRNG entropy source. And with these public and private key, you can do digital signatures and you can authenticate the signatures against the original data. So as you can see, the creating the trust, it starts from a strong key pair. And next we are going to go through the offline tool that uses these cryptographic algorithms. So what you can see here, it's a pretty complicated at the moment, but let's go through it bit by bit. So, and this is an offline tool. So this is what we need to do when we are creating the binary or the bootloader for the digital platform. So on the top of the image or slide, you can see the binary, the gray block labeled bin, so binary, and that is the starting block. So you have generated the binary, which can include the bootloader for the processor, all the necessary stuff, maybe even an operating system or bare metal applications. It can include configuration data for the rest of the platform, including all the peripherals that are on the board. And what we are going to do first, we are going to feed that binary into a SHA-3 algorithm, which is a hashing algorithm. And it takes all of the binary data and creates a small digest of it. And with that digest, we can actually generate the signatures with the cryptographic, asymmetrical cryptographic algorithms. So once we have the digest, we just use the secret key for both of the asymmetrical cryptographic algorithms. And we feed in the digest and use the secret key to generate the signatures for both ECC, traditional cryptography ECC, and for the PQC algorithm MLDSA. And we end up with the signatures from both of the algorithms. And then we are going to take those signatures and the digest and combine it into a binary that we call secured binary, or SBIN, as you can see. And that is going into the non-volatile memory, like you see on the right side. And what is left on the left side is the public keys that we are going to need later. And the other part of the system is, of course, the online tool that is actually running on the ASIC or FPGA or IC in the computing platform. So this is the online tool that is going to boot up the system or verify the boot up image. And we have the secured bin on the left side. So it includes the original binary and the digest and both of the signatures. And what I'm going to go through next, this is all happening simultaneously, which brings a huge advantage. So basically we can just already at this point load up for example, the DRAM data, random access memory, and the all other data already to the external components, external CPU, sensors, etc. But simultaneously, we are going to feed again the data of the binary to SHA-3 algorithm and compute the digest on this online platform here. And once we have the computed digest, then we can just look if it's the same as the digest that was delivered with the secured bin. This will guarantee the integrity of the binary. That's it actually is what it's supposed to be, and we get OK from that digest. And meanwhile, simultaneously, we can also verify the signatures for both ECC and MLDSA. And we are going to use the digest for that one. So we have a little digest that is only a couple of 100 bits long, and we don't need to feed the whole binary to the verification, cryptographic verification. So we need the digest and the public key, and we are going to use the cryptographic algorithms to verify the signatures on both algorithms, on ECC and with pre-hash MLDSA signature verification. And from those algorithms, we get fail or pass. And if both of those are okay, then we have 3 OKs, and we are ready to continue the boot up process while we have already loaded the data to the all necessary parts. Again, let me remind you that that this process happens really fast, because we can do it all simultaneously, and we use the digest for the signature verification. And like I mentioned, this is already a working product, and we are really proud of it. So can you, Petri, talk a little bit where it is used?
Naturally, I just enabled my camera and microphone. Thanks, Valtteri. So quite nice view of under the hood. So this, what we say, authenticated boot is actually now part of our European Space Agency project that we are collaborating quite heavily also with one Swedish company called Front Rate Geisler. And so this product is going to the space. So it can be used on the space, it could be used on the embedded systems or IoT. And so this this project is financed by the European Space Agency partially, and in addition of this authenticated boot or secure boot that we are creating there, we also are creating hardware root of trust, but that's the own topic itself. And so yes, indeed, it goes on the space, and it goes on the space grade GR765 processor. And so that's where our IP core is actually now going to be in the space, one of our IP cores. So let me just check again. So hey, about this space, and so I will show this space once time. So we have this authenticated boot, so it verifies the integrity and the authenticity of the information. But Valtteri, what if actually then we have some secrets there in the binary? So if we have some secret information that we don't want anybody to be able to read, what then? What we could do?
Oh, well, that's an excellent question. And like you mentioned before, the secure boot is combination of authenticity, integrity, and confidentiality, and it can exclude one or the other. So what I just presented, the Cypher secure boot, is so-called authenticated boot only, but it could easily have the confidentiality as well, so all 3, because you could throw in for example, AES in counter mode alongside with the SHA-3 block. So you would just feed the encrypted data to the AES counter, and it would decrypt the data, and nobody would have the access to the actual data if there's any mission critical configuration data or something like that. But then we are talking about symmetric cryptography that needs its own key, and in symmetric cryptography the key is always secret, and that is a little bit problematic, but it can be overcome. And do you have, Petri, any insights on how we even get the public keys to the system? Because we didn't cover that one in my presentation.
Yeah. So that's actually a good point. Is because there's authenticated boots, so secure boot with authentication, and so we need to, so somehow we have to be able, or the user of the system has to be able to provide the public keys for the CPU or the FPGA, because the binary itself has been cryptographically tied for this public key. So we have to have the public keys. And these public keys have to be provided on the system, available for the CPU or the FPGA with some tamper-proof memory. So it means that we have to be able to trust on these public keys. So if somebody would be able to change the public key there and also the binary, then of course we lose the trust on the system. So that requires some kind of tamper-proof memory, like OTP or equivalent, that could be used to store public key or public keys. And so, and as you said, we have to remember that on this scheme we have no secrets. So this is a public key indeed. And the secret keys are a little bit different.
So that sounds like a job for a hardware root of trust. Am I right?
Yes. Actually, yes. I kind of mentioned it a little bit when I said that we have on this project. We are also working with the hardware root of trust, and yes, it's one of the core properties of hardware root of trust is to protect the secret keys and or be able to create the secrets and so on. But that, I think we will have one more webinar coming up. Maybe I don't know when, but we can discuss that later. It's one last topic itself, and on this presentation, Walter, you showed the ECC and MLDSA, and you mentioned about other signature schemes. So is it something that we can change, or is it something that we are kind of locked forever? And is it something that if our customer, for example, would select this current system, is something that's very difficult to adopt? Are we agile to move them forward?
Yeah, of course. One of the points was that we need an agile secure boot. So yes, we are planning on adding additional asymmetric cryptographic algorithms on the secure boot product, including what I mentioned earlier, SLH, DSA, and maybe RSA. RSA is a traditional algorithm, and the SLH DSA is one of the winners in the PQC competition, and these can be and will be in the future releases, and they are basically just pick and replace products. You can have multiple of them, or just the two of just to keep the hybrid scheme still there, and the architecture is already supports additional functionalities.
Sometimes our customers are asking that we change the algorithm something about the security level, or what is, and is it only one security level that is offered? So can you a little bit elaborate about security levels and what it means on this context?
Yeah. So basically there are these security levels for asymmetric crypto as well as symmetric cryptography. So they roughly corresponds the symmetric cryptography AES key length. So there are roughly three categories: 180-bit key, and 192-bit key, and 256-bit AES keys I'm talking about here. So the security levels are roughly correspondent to that. With the MLDSA, the security levels are 2, 3, and 5, and with the ECC, they are actually 1, 3, and 5. So you can easily just parameterize the algorithms for the security level that you want. But of course, there are differences between the security levels, and there can be difference in key lengths and signature lengths, and as well as the performance or the processing times can vary. And that's actually a compromise that you need to have. Do you want a security level, higher security level, or the drawbacks? Can you, Petri, give an example or talk a little bit more about the trade-offs in this sense?
Yes, of course, and so thanks. So I understood that we have all these security levels, and quite often somebody says that, hey, should we go just for the security level 5? And then yes, you could, but the question really is that you have to store these public keys somewhere, or something about the public key somewhere. It means that larger your key is, because that typically reflects even the asymmetric, the larger the key is, the more strength there are. Except if you change from the different algorithm, of course, it might be that SLA's DSA is actually having smaller keys there. So that's one point, is that how much OTP or tamper-proof memory you have. Second thing is that if it's deployed on the orbit, for example, on the satellite, it's something that you can remotely maintain. So how much of kind of second choices you have if your public key is somehow corrupted, or if your public key is somehow compromised. Then more you have security level, it typically takes more computation time. So if you have energy limitation on your budget, and also it takes a little bit more time if you have more security levels, so more security. But even today, I think most of the systems what we have seen would be happy to have even the security level 1 to start with. And this was quantum cryptography is now that we want to go for the hybrid models.
Yeah, that's correct. Yeah. So Petri, we have some real questions from the audience. Can we go through them?
Yes, of course.
And please, you still have time to submit your questions through the Q&A inbox in the Zoom. And if we don't have time to go through the question, please send us an email and we will get back to you. So the first one is concerning can you load the FPGA image to the FPGA using our secure boot?
Yeah, well, okay. So it requires that we need to have some operational code loaded somewhere, somehow. So it means that the trust needs to come somewhere. So if we have FPGA, somehow you have to power up the FPGA with our authenticated algorithm inside there. Or if so it means that the trust is established there somewhere in the FPGA. If it's an ASIC, like a CPU, you might have a hardened block there. So it means that it's already kind of ROM mask on some of the functionalities, except of these public keys that have to be provided there. And then you could be loading other components there. But FPGA and plus FPGA, it requires that the trust is established when you configure or program the first FPGA performing the rest of the system there. So it could be used there, but it requires something else, and it also needs that we are trusting on the FPGA vendors power-up sequences on sometimes.
Yeah, that actually at least partly answers our other question, that can you actually use this to can you include the secure boot into the FPGA and use that FPGA to boot up other system components? So
oh yes, absolutely. Sorry,
may I add that the FPGA vendors, they have their own configuration file protection, which typically use ASGCM, if I'm correct. So it's a basically a symmetric algorithm that provides all of the three, so authentication, integrity, and confidentiality. But it's all under one key, so you have one secret key for all of that. And if the symmetric key is somehow lost or cracked or it's weak, then you lose all of the security aspects. And if you have, in addition, this secure boot, authenticated boot, alongside with that then you will also have the integrity and authenticity from the public key or the asymmetric crypto bits. So it's a good addition to the FPGA providers tools.
That's good point, Valtteri. That's good point.
Petri, you presented the secure boot in space applications. Is there any special concerns or other things to consider when the solution is operating in space?
Oh yes, well this is yes. Short answer is yes, because everything that we do in the cryptography, it means that even if we change one bit anywhere, it actually corrupts the integrity, so it fails on the signature verification and so on. So it is absolutely essential that these algorithms, when they are implemented on the space-grade domain, are using the process that is what they say radiation hardened. And that's not all. You also need to have, because the computations that are done, they're using memory blocks, and memory blocks are not always radiation hardened. Depending on the process that you are using in the space, then there's need for error detection and correction for the algorithms that are run there. Because if you go very heavy radiation belt and you just happen to boot on that time, it might be that you fail to power up the system for a good period of time if those single bit flips happen there. So there are, and that's about one reason why we are working with the leading space grade providers on the CPU.
Yeah.
And FPGA, sorry, and FPGA, of course.
Yeah. So then there's actually two questions a little bit on the same category. So does this limit the performance of the processor or the other components in any way?
No, not. I think because we are doing things on the parallel, and it happens in the beginning. So so when you power up the system, we compute everything very fast in parallel when you are doing all the loading there. So there will be a little bit added time. We are talking about tens or hundreds of milliseconds as an actual time that is caused on the delay there. But the operation of the system, I think it's not changing at all because we are not influencing on the operational environment itself. We are helping on the making the trust on the boot on the platform itself.
Yeah, exactly, yes. And can we, Petri, comment on the boot times because typically there are like we have presented today that there are several components, and does this increase the boot time drastically? Can we comment on that?
So I would say it doesn't increase drastically, and I think I maybe have to revert it back to you. Well, maybe you are the better one to answer for that because you have been designing some of this stuff. So I think we are not talking about seconds. We are talking about
yeah. At least the most time-consuming part is the SHA-3 algorithm, where you have to calculate the digest from the whole binary, and if your binary is really big, then it will increase the time. But I can say that if there's a timing critical application or boot up time is really critical, then you can even have the high-speed version of the SHA-3, and that takes like tens of gigabits of data per second. So it will not likely be an issue there. And like mentioned before, the signature verifications, they only verify the digest against the signature, so it will be a lot quicker than to feed in the whole binary. And then just a reminder for one question that the signatures are for ECC and MLDSA, they are both included in the secured binary. There's one question about that one. So and the digest also, it comes with the binary, and then you verify those signatures in the online system. All right, I think we are already over the time, and it's time to end the webinar. Thank you a lot for the questions and joining us today. And please stay tuned for our next webinar in Cryptography Under the Hood series. It's happening early next year. And in the meantime, please check our website and the previous webinars. And thank you, Petri. It was a pleasure joining you today. And have a great winter, you all. And bye-bye.
Bye-bye. Thank you.